should be ready whenever.
Let me know when.
Go ahead.
Okay. All right. Good afternoon, everyone. Welcome back to our seminar series. As you may notice it, I'm taking the place of our group's big boss, Professor Haochang Luo. And of course, it's my pleasure to introduce Haochang Luo. So Haochang Luo is graduated from Nanjing University of Information Science and Technology in 2018. He began graduate studies at the University of Michigan, where he got his master's degree in 2019 in climate and space science and engineering. In 2019, he has been part of the large-scale tropical dynamic groups, and he has continued to pursue a PhD in atmospheric science. So currently, he is in his 5th year of graduate school, and he's visiting student in our AOS department studying Monsoon low pressure system, which is in fact the title of the seminar today. Energy budget perspective on Monsoon low pressure systems growth by Barotropic and Moisture-Vortex instability. So HC, the stage is yours.
Thank you, Victor. So I know many of you know me as the name of HC, which is the initial of my first name. So my full name is Haochang. And today I'm going to introduce a work carried out by me with Dr. Luo and Dr. Ricky Root from University of Michigan. So let's get started. And by the way, this picture is a photo I took in Puerto Rico. This is where most of our group members come from, and it is also one of the 2 tropical places I have ever been to. The other one is Singapore, which is also a very nice place. So firstly, what is a monsoon low pressure system? Generally, it is a synoptical scale system that forms near the Bay of Bengal and propagating all the way westward and a little bit northward. As you can see from this picture, which is showing the genesis spot of these systems, they usually form near the head of Bay of Bengal here, and it also shows the trajectory, which is the blue lines, propagates all the way westward and a little bit northward, and the termination is usually in the center of India. And by the definition of India Meteorological Department, the surface wind smaller than 8.5 meters per second are defined as the monsoon lows, and in between 8.5 to 16.5 meters per second are defined as the monsoon depressions, and for those stronger systems are defined as the storms. So in our research, we basically look into these 2 different types of systems, but we won't separate them. We just investigate them as a whole group. And generally, this plot is showing the same. The red shadings here is showing the genesis spot, and the contours here is showing the termination. It's just a clearer version of the previous plot. And about the frequency of this type of system, as you can see from this time series, they are about like on average 8 system passes across the area per summer, which is on average 2 per month from June to September, and each of them lasts about 35 days. And this Hoff-Muller diagram is showing their phase speed. So the shadings here is precipitation regressed onto our index, which will be introduced later. And the red line is linear regression of this green block. And you can see that the phase speed is about 5 degrees per day, and which is pretty fast with respect to this kind of synoptical scale system. And if we convert this unit to meters per second, it's usually around 6.7 to 7 meters per second. And and their horizontally can expand to like around 2,000 kilometers and vertically up to 100 hectopascals. So this is a schematic plot showing the structure of this system. From bottom to top, you can see there's a cold core near the surface. And it has like counterclockwise, which is a cyclonic flow on the lower levels. And the maximum wind speed is usually to the east part of the storm. And if you go up higher, this is where the cloud liquid water concentrates. And then goes higher is the warm core. And on the top is large cloud cover. And also, the circulation on the top is reversed. It's more like an anti-cyclonic flow. So after seeing the structure, many of you might be curious about how this system is different from TC, which is the tropic cyclones. So there are majorly like 4 differences. The first one is they have different intensities. For TCs, they usually tends to be like stronger, and for our system is weaker, of course. And the second one is they have different structure. As you can see, that the structure of a low pressure system is often asymmetric, and also is the ring band is loosely connected to the core, and the core is cold on the bottom and warm on the top, which is different from a unified warm core of TC. And they usually have strong vertical wind shear, which we'll be see later in the vertical cross sections. And the third difference is that they happens during different seasons. So as for TCs, they usually happen like in the late summer or autumn or like fall. But as for low pressure system, monsoon low pressure system, they usually happens during summer, which from June to September. And the last one is that they have different duration over the continent, which means our system often have like more than 50% of its lifetime on the land, and it's like have longer duration on the land. And this panel is showing the precipitation difference for the days that have monsoon low pressure systems and for the days that are not having monsoon low pressure systems. So the major difference in the precipitation is around the central India and the Ganges basin area. So the precipitation variation is about like 10% over the Ganges basin area and 27% of the central India. And the precipitation caused by this low pressure system makes up to like 50% of the summer monsoon rainfall over entire India. And this plot is showing the precipitation difference caused by the monsoon depressions and the monsoon lows, which I have used before. They have different surface wind. So you can see that, of course, the monsoon lows have more like, it's more like tend to be influencing the precipitation. And why they are important? Why are we studying this? I think it's like because the precipitation related to this kind of storm. So it will cause like flood and also like drought when it breaks. So and also it relates, this precipitation is related to the fresh water supply in India. And of course India is based heavily on agriculture, and of course like look at the picture on the left-hand side, you can see that it rains cats and dogs and causing flood, which is probably be heavier than today. So based on this background information, we have proposed our question: what is the mechanism that's driving the propagation and growth of the monsoon low pressure systems? So based on this question, we have different answers. Many answers, for example, like barotropic instability and baroclinic instability have been proposed during the past decades. And also like the other theories, for example, the cyst conditional instability of the second kind, which has already been ruled out from the panel, from the list. So also with time passes by, we also propose another theory, which is the Moisture-Vortex instability. And today I'm going to introduce 3 of them and explain why they are possible or not, or impossible in our system. So firstly, the difference between the baroclinic instability and what is the Moisture-Vortex instability. As you can see from these two plots, they are more like vertical cross sections. This is the bottom, and this is the top, and this is west, this is east. So as for the baroclinic instability, there's a low pressure system on the surface, and also a low pressure system on the top. And you can see it's like vertically eastward tilted. And this dashed contours here means the northerly flows. The flows come from north, and this contours representing the flow from the south. So if you look at from top to the bottom, it's more like a cyclonic flow. And this pink arrows are representing the adiabatic lifting, and this is the adiabatic substance. And the teal arrow, the bluish arrow, represents the enhanced convection. So you can see that the adiabatic lifting is happening, it's in phase with this enhanced convection in the baroclinic instability. And of course, the major feature of baroclinic instability is this tilt. And while in the moisture-vortex instability, we don't have the tilt. The system is more like an upright structure, and you have different like high pressure on top. And of course, if you look at the wind directions on top, it's reversed. So this is the flow from the south, and this is the flow from the north. And the adiabatic lifting and the enhanced convection are not always in phase with each other. There's like a peak of this enhanced convection. And if you look at the moisture, there's a peak of moisture in the center of the storm, because when you have strong meridional advection of the moisture from the north, and from north, there's it will cause there's a positive moisture tendency, which means the moisture is increasing in this part, and the convection will be increased because of the latent heat, and the entire system will be strengthened due to vortex stretching. So after seeing that the major difference between these two theories, you can see the most obvious difference is that this is tilt eastward, and this more upright, and this has a high, and this is low, and they have different winds on the high levels. So with respect to the third theory, the barotropic one, so this should be an animation. Yeah, you can see from the animation, it's more like a horizontal plot. So this is more like latitude and longitude. You can see that the barotropic instability is happening because this is like eddies are growing. This is barotropic term in the kinetic energy, but we will be revisiting this back later. So as for this one, oh, I forgot to mention that if we look at these two plots, we always investigate the most static energy, which represents by ampere. It's a combination of contribution from the temperature variation and the geopotential height variation. Geopotential, which is from the potential energy variation and the moisture variation. So, and if we look at the barotropic instability, we often look at the change of kinetic energy because it's the only energy that converts in between mean flow and disturbances in the barotropic instability frame. So here's a wave number frequency diagram showing what's the frequency and the wave number of our system, because our system, as I just said, comparing to tropic cyclones, it's more like a wave. So when studying a wave, we should look at the frequency and wave number of the wave. So I think many of you might be familiar with this plot. It's from Wheeler and Claudia's paper, and you can see that there's obvious signal here at the tropical depressions. So if we, and this was done in the whole tropics, but if we do the same analysis around the Indian Ocean, we can like zoom in and find that the wave number of our system was majorly from like 3 to 25, and the frequency of our system is in between 1/15 to 1/2 days. So it's like 3 to 25, and this is 1/15 to 1/2. And our data set is from Air5 reanalysis data, and this is precipitation panel I'm going to introduce. And so in order to study this kind of system, we need an index to represent the feature, to represent the variability of this system. So we use the precipitation data first. We do the filter in the precipitation data using the frequency domain and wave number domain to get the filter data, and then we do aerial average inside this red box, because this is a plate that has high concentration of precipitation. Also, it's right in front of the monsoon trough, and it has high variability of precipitation. So after doing the average in this red box, we got the low pressure system index, and most of yeah, please.
Reanalysis precipitation, or what precipitation?
Yeah, reanalysis precipitation from Air5. So after having this index, we do regressions and lab regressions, linear regressions, onto this index. So this is a panel that's showing lab regressions of precipitation data onto the index, which is onto the south. The shadings is the precipitation, and the contours is the geopotential height on 850 hectopascals, and vectors are the wings, the zone wing and meridional wings on 850 hectopascals. You can see that from 2 days before the maximum signal day, which is day 0, 2 days before and 2 days after, the system is forming in the east part of Bay of Bengal and move all the way westward from day -2, day -1, day 0, day 1, day 2, and move all the way westward to the central India. And also you can see that the geopotential is in phase with the precipitation. So just to zoom in from day 0 to day 2 of the precipitation data here, and this panel is the shading is showing the most static energy, which I just talked before that why we study the most static energy, because it has information from the temperature and geopotential, and as well as the moisture. So, and this contours here is showing geopotential height on 500 hectopascals, and the winds are also on the 500. If you're comparing these two panels, you can see that the feature of the propagation can be represented by the feature of most static energy, and which means that the moisture here probably is playing an important part in most static energy. And if you compare the contours, this is 850 and this is 500. They are in phase with each other, which means there might be a vertical upright structure inside this kind of system. This is also the most static energy one. So if we do a rooming square of this plot from day -2 to day 2, I only put 3 panels here, but you should know that it's 5 panels. So if we do a rooming square of these 5 panels and put them here as contours, and we calculate the climatological mean MSE, and put here as the shadings, you can find that the contours is kind of following the isoplot of the shadings, which means the movement, the propagation of this system is kind of following the variation of the mean MSE of the climatological averaged MSE. So, like I just said, there might be an upright structure in our system, so why don't we look at the vertical cross sections? These plots are showing the longitude, height, vertical cross section of the system. This is the moisture, the specific humidity, which is Q, showing as the shadings here, from day 0 to day 2. And the contours is showing the geopotential height. The vectors are showing the zone wind and the vertical wind. And you can see that in the positive part of the moisture, which is inside our system, there might be upward motion in the front. And as it moves from east to west, the system is like from upright structure and becomes like tilted a little bit westward on top. So for this one, on the left is also the moisture, and on the right one is the MSE, most static energy. So if you compare these two, you can find that generally they are the same. Same movement, same speed, but if you look at the secondary centers here and here, near the low levels, from day 0 to day 2, the decaying speed of this secondary center is a little bit slower in the moisture than in the most static energy. So which means there might be a little bit difference in the moisture and the MSE, but we won't go that into detail. But generally, we can speak that the moisture is kind of dominating MSE in some processes. So if we comparing these two cross sections with the two instabilities schematic plot I just said, we can find that this vertical cross sections is more similar to the Moisture-Vortex instability instead of the Barotropic instability, because it does not have the eastward tilt and it does not have the low pressure on the top, and the vertical wind is more similar to this one. So right now we have Barotropic instability is not being possible in our system, and we also have a question mark if Moisture-Vortex instability is real. So if we want to solve this question, we should look at the budget of most static energy. So this equation is showing the budget of MSE. This is the tendency of MSE, and this is the zonal advection of MSE. This is the meridional advection, vertical advection. This is the long wave radiation fluxes, short wave radiation fluxes, and surface accessible heat fluxes, and latent heat fluxes. With so many terms, so we plot them as bars here. This is tendency, zonal advection, vertical advection, and etc. So each group, each term that has 5 beings representing that regressions from day -2 to day 2. So after this, any questions? No? Okay. So after this being acknowledged, we can see that the major contributor to the tendency term is from the zonal advection. Of course, these two are a little bit high, but we will talk about it later if we see the next bar chart. But they will be like higher in the next bar chart. Well, this is our major role for this one. Why are we looking at the tendency term? Because to some extent, it explains the propagation feature of this system.
Could you normalize that for each wave? Tendencies all.
So this contribution was calculated by like this term divided by the tendency. So if you look at this one, the tendency contribution to itself is 1. It's kind of normalized, yes.
It's a regression, a correlation coefficient between the quantities, right? You correlate Tm.
Yeah, you can see that. Yeah. So this panel here is showing the movement of our major contributor. The shadings is showing the meridional advection of MSE, and the contours is showing the MSE tendency. You can see that they colligate, they are in phase with each other. So yes, I think this is the major contributor to our tendency term. And if we look into detail of this term, and we continue to simplify this detail into, we can separate them into means and anomalies, like V equals V bar plus V prime, and separate them into 4 different terms. And we do the same analysis to calculate the contributions to this one. We can find that this term is actually the major contributor to the zonal advection, which means the mean MSE advected by the eddies, by the anomalous rings, is major contributor to the zonal advection of MSE. So this plot, the contours is showing the zonal advection, which is the term, this term, and the shadings is showing this term, which means the mean MSE advected by anomalous rings. Just like I have showed this plot before, the variation of mean MSE is kind of affecting the propagation features of our system. Because its contours are showing actually the path of the propagation. And after looking at the propagation, let's look at the growth features of this system. So this is more like a similar bar chart that's showing the relative contribution from different terms to the maintenance of most static energy. So the tendency, the contribution from the tendency is actually showing how this system is like growing or decaying. When it's positive, that means the system is growing. When it's negative, it means the system is dying. And if it is like positive again, that means a new system is forming. So you can see that the major contributors.
What are the 5?
Yeah, the same, like from day negative 2 to day 2 lag regressions. So as you can see here, the major contributors are the meridional advection and vertical advection and the long-wave radiation fluxes. And also, the zonal advection it's generally small, but it's non-negligible when it turns to like decaying stage. So we will look into this these three terms because we have already looked into the meridional advection. So the panel here on the left is showing the vertical advection, and the panel on the right is showing the long-wave radiation fluxes. You can see that in most cases they are like flip signs. They're in phase with each other, but they cancel out in most of the times. And the contours is showing the maintenance of most static energy. So I think that's true that they are the major contributors to the growth, but they cancel out with each other somewhat. So if we do the same step to the zonal advection, like I just said, if we separate this U term into U bar plus U prime and M into M bar plus M prime, we can find that this is a little bit different because we found that the advection by the zonal wing, the zonal jet, which is the climatological mean state of anomalous MSE, is taking the lead. So if you remember, if we look into the meridional advection, it's like V prime times the M bar over the Y. But this one is like flip with like U bar and M prime. So if we plot them these two here, the contours is showing the zonal advection of MSE, and the shadings is showing the anomalous MSE advected by the mean zonal winds. You can say that they are co-located with each other, but there's an interesting feature because on day one, I put day one here because day one is the most obvious decaying stage. So so on day one, the contours are generally following the coastline here. Why it is the case? In my theory, is that this term is affected a lot by the shape of U bar. So if you look at the U bar here on lower levels, for example, this one is on 950 hectopascals, you can find that U bar here is kind of parallel to the shape of the coastline, and which means the U bar is affected by the topography of the continent. So I think that's why this term is sensitive to the shape of the coastline. So now we have barotropic instability being ruled out, and we have confirmed that the MVI is true in this system because the contribution from the meridional advection is really high. And next, we're going to look at if barotropic instability is existing. So this plot, as I just talked before, we should look at the conversion of kinetic energy because it's the only energy that's converged in between the mean flow and the eddies. So if we do the same, like lag regressions from day -2 to day 2, we can find that the movement is pretty similar, but the precision of the maximum and minimum centers are kind of a little bit shifted, like northward and eastward, comparing to the geopotential height centers. But right now we don't have an explanation for that. But if we do like regret of the bar chart, computing the general contribution from different terms, to the tendency of kinetic energy. Like this is a equation for the kinetic energy tendency. So this is a tendency term. This is the zonal advection of anomalous kinetic energy by the mean wings, mean zonal wings, and by mean meridional wings. And this is the most important part. This is the barotropic term, which shows the activity of barotropic instability. And this is the contribution from the potential energy. It's the work done by the geopotential variabilities. And D here is the dissipation term, which refers to the friction. And if we do the same, like calculating the contributions from the terms, we can find the major contributor to the tendency, which means propagation of the system is from the zonal advection. Also, these two terms are also big, but we will look back into that once we saw the growth feature. So if we look at the zonal advection of kinetic energy, which is here, the shadings is showing the shadings is showing the outer, the zonal advection of anomalous kinetic energy, and the contours is showing the tendency. We can see that they're actually in phase with each other. But if we want to look into details of this, like how this U bar looks and how this decay dx looks, we should look at this one. So this panel is showing the kinetic energy itself. So after looking at the gradient of the shadings, we can see that this positive decay over dx to the west side of the storm, and there's a negative decay dx over the east side of the storm. And if we look at the U bar here, the low level U bars, we can see that U bar is positive here. So if this is positive and this is positive in the front and negative behind, so if we time them together, multiply them together and add a minus sign here, you will see that this panels should be flipped, which means the yellowish and the purplish should be flipped. Like this should be yellow and this one should be purple. So it's not equal. Why is the case? Because what we did was the vertical integration. So if you look at the wings on the higher levels, the contours here is showing U bar. You can see that U bar is kind of being easterlies on the higher levels, which means U bar here should be flipped sign. So that makes sense to why the pattern is flipped in the zonal advection. So after looking at the propagation, we should look at the growth features. And the major contributor to the growth is this barotropic term, the geopotential contribution, the work done by the geopotential and the dissipation term. And this panel on the left is showing the barotropic term. And this panel in the middle is showing the potential energy conversion. And this panel on the right-hand side is showing the dissipation. You can see that if we add them together, it's almost equal and reverse of this dissipation, which means the barotropic term and the geopotential conversion might be the source of this kinetic energy, and the dissipation is a major sink of kinetic energy. And if we look at the relationship between the dissipation and the kinetic energy itself, we may find that it's more like a linear relationship. It's documented in the other systems, for example, like MJO, but we don't have a good regression coefficient for this one. because we don't have, we're not using models to do that. We're just using reanalysis data. So after looking at the conversion of kinetic energy, we can see that the barotropic instability is real. And the major take-home message here, the first one is propagation is like kind of affected by the variation in the mean MSE. And the second one is disturbances, the baroclinic instability has been ruled out. And the third one is the strong meridional advection of mean MSE is affected by the strong meridional wing anomalies representing the MVI. And next is the balance between the vertical advection of MSE and the long-wave radiation. And next is zonal advection. It's important to the decay. Zonal advection of MSE is important to the decaying of its system. And the sixth point is that the barotropic conversion was majorly contributed by the potential energy and barotropic term. The last one is that kinetic energy is somewhat to the dissipation. And there's one more thing. So our next step is to investigate whether this is moisture mode. By moisture mode, I mean like whether this system is dominated by the variation of moisture. So I just put this slide here to raise your curiosity. I'm not able to, I'm not responsible for answering it here like today. Just like put three criteria that are representing the moisture mode. The first one is the relationship between the moisture and the precipitation. You can see that the correlation coefficient is pretty high. And the second criteria is whether the moisture is dominating the MSE, which has been hinted, which has been shown in the either the horizontal plane or the vertical cross sections. The third one is WTG criteria, the weight temperature gradient balance in between the heating and cooling. So I'm not gonna answer what they are today. I just put here to raise your curiosity. Yes, we also calculate this non-dimensional parameter, which is the N mode, representing the relative scale of temperature variabilities and over the moisture variabilities. If it is way much smaller than one, that means it's moisture mode. And we have calculated that. So possibly, yes, it is moisture mode. So yes, that's all I have. And if you are interested in our work, and please follow up our group studies. And thank you. I'm open for questions.
It is time for questions. Students, I think go first.
Yeah, please.
So can you explain why a moisture vortex instability, for those of us that aren't that familiar with that term, has the patterns of advection that you saw? Like you have a diagram of the moisture vortex instability, and you saw that meridional.
You mean the bar chart or?
You did a moistatic energy budget, and you found something, and then you argued that that is evidence of a moisture vortex instability. But I'm just trying to understand why.
Yeah.
What about the moisture vortex instability implies that advection pattern?
Yeah, so if we look at the MVI schematic plot here, you can find that the meridional advection is strong because it needs strong meridional advection to contribute to the positive tendency of moisture, which means the southerlies and northerlies are advecting the moisture to the east of the storm.
Okay.
That's,
so there's
I think that's the
advection.
most obvious feature of MVI.
So you're arguing there's meridional moisture advection implied in that figure?
Yeah, yeah,
Where the,
yeah,
okay, where the Q is large or the M is large?
yeah. So basically, this feature here means the meridional advection of MSE is contributing to the MSE tendency.
Okay,
Yeah.
and that's which is mean and which is perturbation? It's a M bar, or it's V bar, V prime, yeah. Remind me
It's
what the
V
term
prime,
was.
V prime times the M bar over dy. So
V prime times the M bar dy. And
So this
why
is,
is there an M bar implied in that picture?
yeah, M bar is showing as the shadings here.
But in the picture, you had illustrated an M prime, right? The picture of the,
This one?
no, the picture of the Moisture-Vortex instability. The schematic, yeah, that one, right? That would be an M prime there, right?
Yeah, yeah, there's a positive M prime. So this picture majorly says that the Q prime over dk is positive here, which means dm prime over dk is also positive. Because
Okay. So this would imply dm prime, v prime dm prime
yeah,
would be the propagation
yeah,
term.
yeah.
But that's not what you're seeing. You're seeing an M bar, or V bar dm, or V prime dm bar dy.
I think you can see that because that's from like advection by anomalous winds. This contour is also showing the anomalous winds features.
Okay, I guess I'm just thinking this is, I don't want to take up too much time, we can chat later, but I'm just thinking this implies a V prime dm prime dy, right? Would be important, this picture, or,
So there's a peak of moisture here. That means the moisture is large here, and also we think that moisture is dominating most static energy. So we think that most static energy is also large here. And what does that mean? That means like why it is large here, because it has positive like advection by the meridional winds. So the meridional winds here, I mean like meridional wind anomalies. So it's still like V prime dm bar dy.
okay. Okay, yeah, we can chat more afterwards, I guess I'm still a little confused about it.
Okay. Question?
If you go to page 24, and I just want to ask, is the land between 60 to 80 east, is that topography? At the bottom, yeah, here. Is it complex topography and there's no data there? And,
I think there should be some kind of topology. So it's like 60 to 80.
yeah, so if the system is propagating east or westward, and if there's some topography there, then you can probably see in the later slides that only the above feature of the voice static energy can propagate through, and the lower feature can be phase away.
I think the other fields, except the mean winds, is not very sensitive to the topology here. I think only U bar is sensitive, because if you look at the cross sections,
Okay, that's what I meant.
yeah, there's actually Yeah, I think the topology works. Like it has effect with respect to the system, but generally to this field are not very important features.
And another question is, can you comment on why the climatology of the moist static energy is much higher northward in like maybe page 28? So that one, the panel, the lower panel, why is the shading like that climatologically? What is the contribution to that?
So the main contribution from moisture, we have moisture plots before, but I don't put here. So the moisture is also very similar to the mean atmosphere. The main moisture is pretty similar to the mean atmosphere. It's here being dry and it's bit here being wet. So I think that's probably affected by the moisture.
Does the geopotential part contribute to that?
It does not very high influence to the MSE.
Because I think it's Himalayan, like at the
Himalayas.
Yeah.
Yeah. It does have like some kind of trivial influence, but not very high.
Okay.
Richard?
Yeah, I was also like going to ask about the same thing. I think like some of, at least like the climatological pattern, would that be related to like the seasonal monsoon thing? Because like so that is why like you have the northward peak in the MSE, I think. So the climatology here, if I'm understanding correctly, it should represent the seasonal monsoon circulation. So like in that figure, if you could go back to the decomposition of the meridional advection. So here basically what we are seeing is that this is dominated by the anomalous flow, right? Like anomalous flow advecting mean MSE gradients.
Yeah.
Okay, so is it right to interpret that the mean MSE gradients are coming from the season, like the monsoon season, northward shift of ITCZ, and then the anomalous flow is coming from the monsoon low?
Yeah.
Okay.
Yeah. So the mean here means the monsoon. Climatological monsoon, and like U bar and V bar means the monsoon jet.
And I was just wondering, from here the contours are the mean flow, right? In the
this
top
one?
panel, in the top panel.
In the top panel? No, the contours as the meridional vector of MSE is like
Okay, the total.
it's
sum.
the sum of mean and anomalies.
Okay, makes sense.
Another question?
I guess I'll ask one more. Can you like use similar way to detect the eastward propagation maybe when monsoon retreats in the winter?
What?
So you have seasonal monsoon, and here is the monsoon propagating westward in the summer. Is there a similar technology that can technique that can kind of analyze the eastward propagation or some feature in the winter?
I'm not sure about the.
My understanding is, like I'm not exactly sure of how the monsoon retreats, but my understanding is that you have basically like dry air intrusion coming in from northwest, so that kind of like kills this westward propagation rather than there being like an eastward feature which makes it go east. That is my understanding, but it could be very wrong.
We have another question. Yep.
You noted that the E prime and Y, the contours look very similar to the mean state, and so is it it right to say that this moisture mode is just kind of a modulation in the intensity of the monsoon? Or is it, I mean, when I look at that, the contours show a maximum to the south as well? Is it more like the monsoon and maybe some surges to the south? Or how would you put, since they have the same pattern, it seems like it's just a modulation of the intensity of that monsoon surge.
Are you talking about the bottom plot?
I think this one.
I think-
No, not the lower band.
Oh, this one?
The shading is the mean noise.
Yeah, the shading is the main. I think this plot is just showing that the monsoon variations might be the source of energy that contributing to the movement of the disturbances, because the trajectory is parallel to the isoplot of the monsoon mean MSE. So I think so the energy conversion could potentially happen in between the mean monsoon and the disturbances. But I'm not sure whether the variability in the south could be affecting.
Okay, I think we have time for one more question. No question?
So what would that budget look like if you didn't have a moisture vortex instability? Like how would that budget tell you that you didn't?
If we don't-
The moist static energy budget. Just coming back to my question, I'm just trying to understand why the way the budgets work out tells you it's a moisture vortex instability.
So if we don't have MVI, this term probably be small, and you probably drawing energy through the other types of instabilities, for example, the barotropic instability. So I think UW-AOS has a paper that's showing barotropic instability might be the core energetics that giving energy to these disturbances.
So
So
what
that
would-
also being potentially correct.
So what would the budget look like for a barotropic instability? You wouldn't have an M prime DT, or
I think that should be verified by modeling data, not reanalysis data. But my guess is that this term could potentially be small, and this tendency term could also be small.
okay, so a small tendency return.
Okay, I think time's over. Thanks so much again, HC.